Hi class, in this video I'm going to be reviewing section 20.3, Coulomb's law, out of your textbook. Coulomb's law is an equation, it's this equation, and what it's used for is finding the magnitude of the electrostatic force of attraction or repulsion between two charged particles. So what the equation says is the force on a charged particle is equal to a constant, K, that's the electrostatic constant. It's got a value of 8.99 times 10 to the 9, and then it's got some units here attached to it. And it's a constant, it's just a number we put in to make the equation work, to get it in the right units. And then, so it's that number times charge 1, which is going to be in coulombs, times charge 2. If either of these are negative, you just take the positive of the value. That's what those absolute value bars are for. And then we divide by the square of the distance, so how many meters the two charges are apart. So looking at this equation, the factors that affect electrostatic charge are the value of the two charges themselves and the distance between them. Okay, so we've got a picture here that illustrates the types of problems you'll see with Coulomb's law. Like I said, it's the force between two charged particles. So this equation gives us the magnitude, and then the direction you will have to figure out from the problem. So force is a vector. We know it has a direction and a magnitude. So like in this example here, they're both positive charges, and so they would feel a force away from each other. We know that like charges repel. And so the direction of that vector you would have to assign, but Coulomb's law can help us find the magnitude. Okay, and then remember that opposite charges feel an attractive force towards each other. Another thing to note is that the force each particle feels is the same, no matter the charge. That's because of Newton's third law, and we will talk about that in a little bit. Okay, looking at the first example here, it says the charge of sphere 2 is twice that of sphere 1. Which vector shows the force of 2 on 1? So this vector here shows the repulsion from this particle on this particle. And it asks us what vector would go with number 1. Now you might guess that the vector for 1 would be A, that it would be longer because 2 has more of a charge, and so there'd be more of a repulsion. The correct answer is actually B, because the force of 2 on 1 and the force of 1 on 2, those are third law pairs. So Newton's third law says that every force has an equal and opposite force. With electrostatic charge, it's the same way. So even though these particles have different charges, Newton's third law says that force between them has to be the same. And that matches what we know of Coulomb's law. We see that the force of one on another, it's equal for both because it's actually dependent on the magnitude of both charges. Okay, next one says the charge of sphere 2 is twice that of sphere 1, which shows the force of 2 on 1, so that other vector that's not on the charge, if the distance between the spheres is reduced to r over 2. So it's asking if we brought these closer together, twice as close together, what would the new force vector be? Well, before that distance is reduced, the force vector is going to be the same as its third law pair. So it's going to look something like that. Now, if we brought these closer together, that force is going to increase. And we know that those vectors are going to be third law pairs with each other. The question, though, is how much is it going to increase by? Well, according to Coulomb's law, if distance decreases, force increases. So looking back at our equation, force is proportional to 1 over the distance squared. We know that charge and the electrostatic constant are in there, but if those are held constant, if force increases when R decreases. So I think C would be the best answer. Yeah, so it'd be asking for the vector that would go with this guy. So C is the best answer. Okay, next one. It says, in each of the following cases, an identical small positive charge is placed at the black dot. In which case is the force on the small charge the largest? So we've got several different charges here. The 2q1 is more, so it'd be like double the charge. And then we also have a dot that shows how close a second charge would be to it. So we know that the one that's closest with the biggest charge would have the most force. And in this case, it's option C. We see that the distance is r and the charge is 2q. So we've got the closest, distance, and the biggest charge. Okay, and we know that because Coulomb's law says force is proportional to 1 over the distance squared, and force is proportional to charge. Okay, next one. It says, in each of the following cases, an identical small positive charge is placed at the black dot. In which case is the force on the small charge the largest? So we've got multiple charges in our picture, which is new. We need to draw force vectors, multiple force vectors on the black dot, because one's going to be from one charge, the other's going to be from the other. So it says that this is a positive charge. So if we think about how far it is away from this negative, it's pretty close. They're going to be attracted. So I'm going to draw a vector for this guy here. Okay, and that's due to this charge. They feel an attractive force. And then this positive one is an equal distance away. And so it would feel a repulsive force of the same magnitude. And then if we add up these two force vectors, our F net is going to be twice as long, maybe something like this. Okay, for B, again, this is a positive charge, so it's going to feel an attractive force towards this guy. And then it's going to feel a repulsive force due to the positive charge, but it's farther away, so the repulsive force is going to be less. So F net probably looks something like this. Okay, for C, again, this is positive, so it's going to feel a repulsive force from this one and a repulsive force from this one. But this one's farther away, so the repulsive force is going to be a little less. And then if we add these two vectors up, our F net maybe is this size. Okay, for D, the force due to this guy is going to be this way. And the force due to this guy is going to be that way. And they cancel out. So F net is 0. Okay, another question asked us, which is the force, in which case is the force the largest? That's for A. You'd see we'd have the longest F net. And it doesn't matter if it points right or left. It's asking about the magnitude of the force, which is the length. All right, we have a few more to get through. All right, this one says, what is the direction of the net force on the charge at the lower left? So this one. And then it's asking A, B, C, or D, which one is the net force. So, let's see here. Do I want to redraw this? Yeah, I'm going to redraw it over here. So here's our positive charge. And then we've got this guy straight up above, this one, which is double, and then this one here. Okay, so I'm going to draw my force vectors one at a time. Remember, this is the one we're looking at. So if this one is right above it, and they feel a repulsive force, that vector is going to point down. And then this one is going to point left, same length. And then lastly, this one is same distance away. Well, actually, I guess it would be farther because it'd be the diagonal of a square. But it's double the charge. And so maybe it'd be something like this. Okay? And so if you add these vectors up, you would get a vector that looks like B. Down and to the left is the net force that that particle would feel. It would accelerate in that direction. So B is the best answer for this one. Okay, 20.14, which is the direction of the net force on the charge at the top? So we've got, I'll redraw it, a positive, and a negative, and they're all the same size. So from this one, it would feel a force up and to the right, and then this one, it would feel a force towards it, which is down. And so F net would be this guy. So best answer for this one would be D. Okay. I put 2 calculation problems in this packet. You're going to need Coulomb's law, which I'm going to write down on my paper. F equals K, which is a constant again, Q1, Q2 over R squared. Okay, so keep this in mind. I will give that to you on a test. You don't have to memorize it or anything. Okay, and then they give us a nice little diagram. So let's read this question. It says 2 10 nanocoulomb charged particles. Remember, nano means is times 10 to the minus 9. So 2 10 nanocoulomb charged particles are 2 centimeters apart on the x-axis. What is the net force on a 1 nanocoulomb charge midway between them? So we have a picture here showing our 2 charges, and then our test charge, this guy's 1 nanocoulomb. And we know that it would feel a force repulsed by this guy, and then repulsed from this one in the other direction. And then it's asking what the force is halfway between them. Okay, correction here. There was 2 questions here, A and B. We're looking at B. So instead of 2 10 nanocoulomb positive, there's 1 positive and 1 negative. So this is our situation here. Otherwise, F net would be 0, right? Okay, we want to find this one. Okay, so if it was positive on the left, it would feel a force this way. If it was negative on the right, same direction, and we want to find F net. So we know that these 2 forces are equal because these are all 10 nanocoulombs, positive or negative, doesn't matter. And Q3 is in between them, so same distance. So we can write an equation that says F net equals F1 on 3. We'll just use their same notation here, plus F2 on 3. And then we know that these are equal because they have the same distance and the same magnitude of charge. Okay, so I'm going to just find one of these individually, and then we'll double it and have our answer. So F1 on 3 is equal to the electrostatic constant, so 8.99 times 10 to the 9th times charge 1, which is 10 nanocoulombs, so 10 times 10 to the minus 9. Okay, and then times 1 nanocoulomb, so 1 times 10 to the minus 9. I should have written 1.0, whatever. We'll just remember to put 2 sig figs in our answer. Cool. Actually, 1 sig fig, because this is 1 sig fig. Okay, and then we're going to divide by the distance between them squared. So 2 centimeters, halfway between them would be 1 centimeter. So 0.01 meters squared. Okay, if we type that all in our calculator, we get 9.0 times 10 to the minus 4 newtons. That would be one of the force vectors. And then we want to double it to get an F net of 1.8, rounding to 2. So 2 times 10 to the minus 3 newtons. Okay, sorry about the confusion there, you guys. Okay, so Coulomb's law, pretty easy to plug everything in. I think the hardest part of these is figuring out the direction of the net force given a diagram and kind of reasoning your way through that. But the equation's pretty simple. You just plug in the constant, the 2 charges, and then the distance. Okay, and then do not forget units. Newtons, it's a force. Okay, we're going to do one more example problem, and then I'll set you loose on the book problems. Okay, this one says 2.10 gram honeybees each acquire a charge of 23 pascals as they fly back to their hive. They approach the hive entrance. When they approach the hive entrance, they're 1 centimeter apart. What is the magnitude of the repulsive force between the 2 bees? How does this force compare with their weight? So I guess the bees, when they're flying around on their fuzzy little bodies, they collect static electricity. They're each positively charged, and so then when they get near each other at their hive, they're going to experience a repulsive force from each other's bodies. By the way, pico means times 10 to the minus 12. Let's draw a picture. So here's one bee, here's the other. It tells us that they're a centimeter apart, so 0.01 meters. Each of them weighs 0.10 grams. We're not going to use that in our calculations. We know they're going to feel an equal and opposite repulsive force from one another that we want to find. And then we're given the charge of each bee, which is the same. It's 23 times 10 to the minus 12 coulombs. Okay, let's figure this out. So remember, we have F equals K Q1 Q2 over R squared. That's our Coulomb's law equation. So I'm going to plug everything in. 8.99 times 10 to the 9th times, and then instead of writing 23 times 10 to the negative 12 twice, I'm just going to square that term. Okay, we're going to divide by the square of the distance, so 0.01 squared. And we get 4.8 times 10 to the minus 8 newtons. Okay, and then this is on each bee. Okay, the second part of this question says, how does this force compare to their weight? So, question is, are we going to see the bees accelerate? Is this even on the same order of magnitude as the bees' weight? So, the bees' weight, that's our gravitational force, mass times gravity, right? We get 0.1 grams would be 0.001 kilograms times 9.8 meters per second squared. I need a calculator. Looks like we get 9.8, I guess I could have done that in my head, oh well, times 10 to the minus 3 newtons. So that's their weight. And then comparing it back to this guy, If we divided it by the force that we found, we find that it's 200,000 times greater. Okay, so the repulsion that they feel is really, really small compared with their weight. So we probably wouldn't see them accelerate any appreciable amount. Cool. So your guys' homework is to fill out the workbook problems. I gave the sub the answer key, so you can check your work. They're all qualitative, so you're not going to have to do any math. Tomorrow you're going to do practice with Coulomb's law, the types of calculation problems like we reviewed in class just now. So that'll be tomorrow. Today's homework is qualitative.